Hi everyone, so welcome back to our YouTube channel, Becoming a ROS Developer. Today we've got one of our students, Joshua, who has just completed the course ROS 2 Basics in 5 days using Python. So he's going to demonstrate his code on a real robot, and then after that he will take us through his code to explain what he has done, how he has managed to accomplish the task, and then at the end we'll have him answer a couple of questions to really get into the details and see how he managed to do it. All right, I will hand over the floor now to Joshua so that he can share his screen and we'll be able to see what he has managed to accomplish. All right, Joshua, over to you.
All right. So as we wait for the robot to connect, let me share my slides real quick. All right. All right. So hi everyone, my name is Joshua Onuegbu. I'm a University of Houston student. Uh, this project is based on ROS 2 Basics in 5 days course, and it implements three components: topics, services, and actions. So topics are like sending continuous data. So topics are open-ended. So you send continuous data without any expectation of feedback. And then services, the way services work is it's more close-ended. So you have a definite start point and a definite end point. And then actions are a bit more long drawn out. They are also close ended, but the tasks are much more complicated. And this one applies to the odometry recording. Now for the problem statements, what we're trying to do with this project is to create a robot that can autonomously find a wall and navigate find a wall and navigate use that to navigate its environment, not just the wall, the obstacles in its environment to navigate and know where to move. It uses recording and of its trajectory and its position data, and there are some challenges that would need to be overcome to do something about to find a problem to this, and that's wall detection, starting wall detection. Wall detection, here we want to find the obstacle and use that as a leverage to know where to go in the environment. So we are using sensor data to distinguish walls from obstacles from everything to know where to move. And then distance regulation, we use the laser scan and we use control algorithms to know where to move and where to stay and where to turn in the environment. And then corner navigation, this is important because you wouldn't want the robots to move along a straight line, and then when it approaches a corner, it just goes off track and it hits a wall or something. So this is another problem that we need to do that we're focusing on. We're trying to do something about here. And then data connection analysis. This one is based on the odometry recorder, where you collect the data and you use that to analyze the robot, know where the robot is, track its position from its environment, from the wall, from the obstacles in its environment. And now, solution overview, how the steps that we're taking to solve this project. First, we implement a laser scan subscriber to receive and process the wall detection. And then from there, we develop a ROS service that analyzes scanned data and executes an alignment. So to position the robot parallel to the nearest wall. So this one is done by the wall finder. And then step three, we create a control loop that continuously publishes velocity commands. This one is done by the wall follower. So we control loop that publishes velocity commands. By velocity commands, we mean um, movement, right? Movement, the movement of the robot, the actual movement based on lasers readings that's been done in step one. And then in step four, we design an ROS action server that records the robot's position. This is the odometry thing, where we check the robot's position and everything. And then in step 5, we create a comprehensive launch file. This is the main.launch.py. This is the actual one that launches, that compiles everything and makes the thing run. Now, since the system architecture, starting with the whole thing begins with the wall finder. It finds the nearest wall and it aligns itself properly. And by properly, it means, according to the prompt, it means the robot having a 90-degree angle parallel to the wall. We want it to be on the right hand side of the wall. Um, and then once it's completed, we send the signal wall find equal to true, and then we transition to the wall follower. The wall follower and the odometry recorder, they work together. So what the wall follower does is, this is actually the main node though. What this does is that it starts the moving along the wall. It's actually what makes the robot move. It uses the laser scan data to track its position and make corrections. And then it handles all manners of obstacles and corners and emergency stops, everything dynamically, adaptively. And then from there, it runs continuously. And then it runs with the odometer recorder. What the odometer recorder does is that it tracks the robot's movements and the total distance traveled. And then, if in the event that we implement we want the robot to just move one lap, we can tell the robot to stop after that one lap if we implement that into the code. And then, it complements the wall follower, and they work together. Now that's for the control loop, and then from the flow chart, um, it's basically what I explained. So we start with the launch file with the launch thing, start main.launch.py, and then it moves on to wall finder. The wall finder does its thing. It checks it waits for the laser scan data. Once it gets something, it finds the closest wall, then it rotates to face that wall. It moves towards that wall, aligns with the wall. If it's the alignment is not good enough, it tries finding that wall. If it's the alignment is good, then it sends that wall found thing equal to true, and then from there it goes straight to the wall following. And then it's, with the laser scan data, it gets distance readings, emergency stop. So emergency stop is when the robot gets too close. We don't want the robot to get into close to the wall, and then it develops something. It's develops a problem or something. We want it to be at a safe distance. So if that emergency stop, if we encounter that emergency stop thing, we turn left to avoid it. If there's no emergency stop, then we stop, and we adjust to the wall. And then if it's too close to the wall, we turn right. If it's not close, we turn left. And then from there, we move forward. And the odometer recorder does its thing. It's computes distance traveled, and then returns to start and ends recording. So let me just demonstrate how everything works with the robot. Enough talking. Let me just go straight to demonstrating how the robot, how everything works. Let me share my screen here. Okay. Now, okay, let me just. Okay, so robot. Okay, so let me connect this here. Okay, let's build the file here. It's connecting. Let's build the file. Okay, just connecting. Okay, so these are the three main components in.
Hi, Joshua.
the process, and then from there, these ones come in, and they work together to make the robot work. So we find the wall with this one, and then we tell the robot after we found the wall, then we tell the robot to move to actually move. And with this one here, this is the real deal. This is the real thing. This is what makes it work. And then the odom recorder records um, the position data. So now, okay, let me check my robot. Let me check the streaming is working now. Okay, let's reload this. Okay, let me disconnect it again. Okay, connect it back. All right, as it's connecting back, let me just run through. I'm not sure what's going on with the network today, but as it's connecting back, let me just explain. Oh wait, is it connected? It's not. Okay, let me just explain what's going on here. Starting the wall finder. Okay. Okay. So the wall finder, what it does, like we said before, is that it scans the environment with the laser to find the closest wall. So it does that by subscribing to the laser, and it's done here. Where is that? It's done here. It subscribes to the laser on the robot, and then from there it finds the shortest distance um, from the robot, and it does that here. This is where it
Hi, Joshua. Can you hear me?
done. It's done here. Target angle. It's done. I think it's okay. Target angle. It's done here. Yes. Yeah, this is what does it. It calculates the angle to the wall, and then let me just break this down a little bit. So this one here is the starting angle of the scan. This one is the index of the shortest range in the array, and this was multiplied by the increments. This is just uh, the the breaks. So the increments, whatever the breaks in between the angles, yeah. So that's what that does. So the result at the end of the day is that it finds the direction of the nearest wall with the angle. It finds the direction of the nearest wall, and then from there we go to the robot rotates to face the wall. In here, the robot rotates to face the wall. How that works is that we use this here, target angle, this one here. So it publishes tweets messages to command veil onto the front laser. The front laser is 0 degrees. Onto the front laser matches the shortest range. So and the result is that the robot faces the wall. And then from there, we go to um, approach wall here.
All right.
What this does is that it moves the robot to 0.3 meter from the wall, which is the desired distance that we wanted, 0.3 meters. So
Mm-hmm.
it moves the robot to 0.3 meters. It makes the robot approach the wall 0.3 meters using this one here.
All right.
Where is that?
Joshua, if you can
Yeah.
hear me, you
Yes.
can hear me, right?
Yeah. Yes.
You've got 5 more minutes, so I think let's try again attempting to connect to the real robot and see if we can get
Okay.
it going.
Oh. Okay. Okay. Something's wrong with network today. I'm not sure why this is not connecting. Let me disconnect this again.
All right.
Okay.
Yeah, it's taking a little long, but let's give it time.
Yeah. Yeah. Let me reload the page. Maybe that will fix it.
All right.
Yeah. Okay, so let me continue with the explanation so that I don't know. So yeah, so everything works together. From there we go to align the wall, aligning the robot of the wall, and then we end with the the find wall callback. So I'll show you the find wall callback very quickly.
Mm-hmm.
Um, it's connected. Okay, it's connected. Um, Yeah, there's a problem with the server this morning.
I see.
Okay, let me go.
Yeah, we'll try to get it
Yeah,
resolved so that it doesn't take that long to connect
yeah.
anyone.
But I can show you the video that I was talking about.
Yeah,
The
sure.
evidence that it's what.
Sure.
Okay, should I show you right now?
Would appreciate that. Yeah, let's go ahead. Sure, you can show it
Okay,
now.
okay, all right. Okay, okay. Mhm. Okay. Me. So I'm launching the file there with that.
All
That's
right.
it. Yeah, on the screen.
It's
Yeah,
very smooth. What
yeah.
control mechanisms did you use? Did you make it PID controller
I just used I work mostly with velocity,
with
velocity calculation,
say that again?
mostly velocity. Velocity. Let me
Oh, okay.
pause the video.
All right.
So I work mostly with velocity. Yeah,
Okay.
yeah,
All right. So you were like hard coding velocity using
yeah. I was
constant
hard
time.
coding. Yeah, just to make it smooth. Yeah,
I
because
see.
when I first started, it was really terrible. Okay, let me
Okay.
stop the video.
All right.
So it was really terrible. Yeah. So I had to hard code it. Okay, let me go back to. How much time do I have left for the presentation?
You've got 5 more minutes. I would have to ask you questions in those
5 minutes.
5 minutes. Yeah. So,
Okay, you can ask me questions now. But
all right.
um,
Yeah. But
let me give you a minute to just run through the wall over. Just a minute to just
okay. All right.
go over. Yeah. Yeah. So this one, what this does is that what this does is that it makes the robot actually work. It makes the robot move through the navigate through everything.
Mm-hmm.
So something I kind of realized one of the thing I think one of the reasons that the robot is moving so smoothly is that when this emergency distance is higher,
Mm-hmm.
this thing here
Yeah.
is higher than the self desired distance. It the robot it's the robot when it's turning corners, it stops frequently. But
Oh. Okay.
I discovered that by accident. When I reduced this value here,
Mm-hmm.
so if it was 0.35 before,
Yeah.
the robot was not.
Smooth.
Yeah, so I reduced the
Yeah.
value. Yeah, so
Very
that's
good
something I wanted to
observation.
point out in this. Yeah, that's something I want to point out in here. And
Can you at
um,
least give a small explanation why you think that is? Did you try to think about why it
yeah,
works that way?
yeah. So the intuition behind this is that um, when the robot sees a desired distance,
Yeah.
it wants to keep going, but when the emergency stop distance is higher, it stops the robot and it makes it stops it
Uh,
makes it stop and keep. Yeah, that's
wonderful.
why yeah, so that's why it's behaving. So it was something I discovered when I was I was trying to adjust to make the robot smooth because it wasn't smooth at all. It was misbehaving like so. That's one of the things I discovered. Um, Another thing I discovered, well, it wasn't a discovery necessarily,
Mm-hmm.
but one way to test for the odometry recorder
Mm-hmm.
is wait, is it here? Oh, I didn't update the code, but you can actually test the odometry recorder by implementing a one lap thing so that um, it's the robot stops after a certain amount of time.
All
So
right, all
that's
right.
something else I discovered when I was yeah.
So,
So it's something else I discovered. So that's it.
after a
Yeah,
certain amount of time or after a certain
yeah,
amount of distance, so you'd have to estimate the velocity of the robot. Okay, I see what you mean there.
yeah,
Mm-hmm.
yeah. Yeah.
All right, I see there's
So I
also a
think
value for KP, so there is some form of proportional controller in there, is that right?
yeah, yes,
Yeah,
yes,
okay,
yeah.
that, yeah,
So that helps with the corner thing, the corners and yeah,
yeah, that also does help. That also does help. Then it doesn't respond with a jerk every time, it responds proportionally to how
yeah,
close it will be,
yes,
right?
yes, yeah.
Um, all right, so I think let me ask you some questions. Did you still have anything you want to talk about? Because I think you've got about 3 more minutes.
No, I have nothing else to talk about. I mean, those are the highlights of the things I noticed while creating the
I
code.
see. I see. Very
Yeah.
nice. Thank you very much for making that contingency plan and recording your robot working. It shows
Yes, sir.
that you had time to try it several times and watch it work. That is
Yes, sir.
very good on your part to document your own progress like that. Um,
Yes, sir.
all right. So on the questions part, I want you to explain a little bit why you had to use a service on the wall finder, right? You had a choice. You could use
Yeah.
an action, you could use a service, you could use a topic. Why pick a service in this case? What's the theoretical underpinnings behind that?
It would be behind the wall finder.
Yeah, behind picking a service is a form of communication for your wall finder, right? Why did you make it a service?
Yeah,
Um,
yeah. So the reason I made it a service is so that I explained earlier that a service is is closed ended.
right,
So I observed that the robot was misbehaving, and I needed to find a solution because I needed to make sure the robot works.
all
That's
right.
the point.
So
So I
so
needed to hard code.
it was misbehaving when you were using what? You were using topics. What were you using as a channel for
When I
communication?
was using was it topics? I think it was no, not topics. I think it was I think it was topics I was using when I was coding, but it wasn't responding well. So it has been a long time since I changed, so I don't really remember the details like that.
All
But
right, I see,
yeah,
I see.
yeah, yes.
Because
I
all
just
right,
want to
so
make the robot work.
the
Honestly.
thing is, when you use a service, that you have a server and a client, right? So when a
Yeah,
client sends a request, then the server has to respond in some way, right? It
yeah,
has to respond to that request, right? And then once there
yeah,
is no more request, then the server will stop broadcasting data, right? So um, ideally, right? Ideally, your explanation will be along the lines that because I only have to check, right? I only have to
mm,
check for the wall once, right? You are trying to find the wall
yeah.
at the very
The
beginning,
wall,
right?
yes.
Once you found it, then there's no need to have your wall finder to keep looking for the wall because now you are
Mm,
using the wall follower, right? So the wall is found
mm,
already, so your wall follower is
mm,
now taking over and following the wall. So
mm,
you cannot be still looking for the wall in that case because you've already found it, right? So it's better to use a service client kind of communication channel, right? So typically that
mm,
would have been um, a better explanation, but I see what you mean. Then
okay.
the other thing that I wanted to ask you is the emergency stop, right? How did you
Yeah.
implement that? Did you just put figures to say if you go beyond this figure close to the wall, or if you are too close to an obstacle by this much a distance, stop, or there was some more logic to it?
So what happened was that you know. in the prompt for this project, it's
Mm-hmm.
mentioned that they wanted the desired distance of 0.3 meters.
Okay,
Oh,
so
sorry, 0.3 meters. Yeah.
so that's the desired distance between your robot and the wall, or between the robot and
Yes.
what is in front of it.
Yeah, no, it's between the robot and whatever is in front of it. Because when I tested this robot, it
Mm.
was not just responding to the wall, it was responding to other obstacles in the environment. So it's
Right.
between the robot and other things in front of it. So yeah, so how I implemented this is that I made a little research on how to. I made a little research on the emergency distance, on how to make sure the robot does not collide with the wall, and how to optimize that with making sure that it stays a safe distance from the wall.
Mm-hmm. I
And
see.
as I was struggling because this is where I'll spend so much time on this part of the code, trying to make sure that everything works well. And
Mm.
that's how I found out about this emergency distance thing.
Okay. Okay. I see. So
Yeah,
again, on that same note, right? Can you show me
yeah.
your code section where you were dealing with scan data, right? Because if you are implementing a wall finder, you have to be doing some form of processing on your laser scan data. Can you show me where you did that and walk me through it?
Okay, lasers. Okay, okay. Where is that? Where did I put that? Mm, I think it was in
Somewhere.
Wall Finder. Yeah, it should be in Wall Finder.
All right.
Yeah. So making sure that these are okay. Found the was yeah. So I think this is where it started. Laser scan. So okay, yeah. This is where it started. Rotate to face wall.
Mm-hmm.
So rotate to face wall. You're starting from here,
Mm-hmm.
and then this one checks the angle. So if the angle is zero, so the 0 degrees, like I said earlier,
Mm.
is the angle, is the one in front, directly in front of the robot.
All
So
right.
if
So
it's
that's like
turned,
your front index.
yeah, the front index. So
Okay.
if the robot is yeah a certain angle, it turns the other way and all that stuff.
All
So it
right.
keeps going on like that. And there's so many things I implemented here that it's hard for me to. So many things I put here. Okay, and it stops following. Okay, yeah. So this one actually implements the 90 degrees thing to make it turn right. So here, twist sends a twist velocity message,
Mm.
and then it turns the other way. This is 0.3 um, meters per second.
All right. So
A
if
centimeter.
you
Yeah.
if you're um let's say, how do you check the left index, for example, right? In terms of how
Yeah, the left.
the ranges data that you're getting, right? How would you check your left index in a similar
Yeah.
way that you did for the
This
right?
is yeah. This is what I used to check the left index.
All right, I see.
This one. Yeah. And then
Okay.
for the right, it checks the right one.
All right, so a negative.
So it's all based on velocity. Yeah.
All right, this is interesting. Determine. Mm-hmm. All right, all right. Um, let me look. Just hang on there. I wanna.
And
Okay,
can
it's
I?
quite nice the way you implemented it, right? You're taking in ranges and making sure that you split them into different sections around your robot
Yes.
to be able to figure out
Yes.
where is my zeroth index, where is whatever you call the 90-degree angle to the left, 90-degree angle to the right.
Yes.
All right. Let me see if I have any
Can
questions.
can I can I check if the robot is working now?
Let
Because
me.
I think I still have something.
All right, just hang on one sec. Yep.
Okay.
We could probably be out of time, but I'll give you one more minute to just check.
Okay. Because I really want to show that the robot is working. I just don't know why. I don't
Yeah,
know
it's
why this is
great.
not connecting. I was so excited to show it. Like I was so excited
Yeah, it's a good thing
and
that
to
you
hold
recorded it, so you don't.
really immersed. What do you say?
I'm saying it's a good thing
Oh,
that
it's
you
not
recorded
working.
it.
Oh,
So don't beat yourself up for that too
yeah.
much. It's we have seen how you have managed to do it, and congratulations. So well done on demonstrating your project and taking us through it theoretically and showing us the demonstration, even though it wasn't live. But we promise we'll get that resolved. Okay. All
Yes,
right.
sir.
So let me just wrap up, and then we can finish our meeting on Zoom. All right, so this was Joshua's project, and would like to encourage everyone who would be keen to try one of the courses that we offer certification on, and you would be sure to take your knowledge through the paces and try to understand in depth how your code will work on a real robot. So until next time, keep pushing your ROS learning. Bye bye.